Nice. So,
Whenever you're...
okay, I am starting. Good afternoon. My name is Anna Maria, and I will present you our work along with Fauzi, Daphne, Sabine, Doris, and Nadine, the solar green. So, what are the problems that we actually tackle? It is the decrease of the efficiency of the PV because of overheating, the lack of surface on the roofs for implementing the PVs, and the urban heat island effect. What is our solution? A module that combines the evaporative cooling effect of plants in order to cool down the backside of the PV. And here it is how it will look like when we apply it inside the city. So, where it all started, we will go to Spain, where we will have the Mediterranean climate and the high temperature and low relative humidity. These conditions are very important to have potential for improvement in the product. It will be placed in the blind facades of the apartment blocks in urban centers such as Madrid. Our main principle is the evaporative cooling effect of plants. It is part of the natural circle of life and achieved through the leaf surface. And now about our first decisions. The shape of the module, we investigated two different ones, the hexagon and the rectangle. We decided that the hexagon is better because it interlocks with more neighboring modules. We can combine the substructure into neighboring columns, and moreover, we can fit more plants per surface. Regarding the angle of the PV, we decided to go with a vertical one because when tilted, either the panels are partially shaded or they need to be in bigger distances in order to avoid this effect. Regarding the shape of the PV, we chose to go again with the rectangle one. It offers a better proportion between the solar cells that we can fit in it and the amount of surface that we have. Moreover, it gives us the possibility to put it in different positions and thus create more patterns inside the sheet. Now about the support of the PV. We chose to go with the one connection in the center. Although with 4 connections, it will be more steady. We chose that because it is easier to assemble and disassemble. It doesn't block the view of the plants, and moreover, we can distribute the wires through it to the back of the module. And now let's have a closer look in the wiring. Inside the PV, we chose to have the parallel connection in order to have the bigger efficiency. And then when the wires go behind the module, they concentrated and charge controllers. Afterwards, they will be distributed in the electrical grid of the building. As you can see here, our PVs partially shade the plants that we have. So we go with a shade-resistant plant, which is the Pachycandra. It has a low growth rate, which ensures that won't need a lot of maintenance, and the leaf surface is big in order to have more evaporation. The water flow is achieved through the hydroponic system. The water flows from top to bottom inside the modules, inside the buckets that we have in the modules. Then we experimented with these principles and we concluded in our final model. Let's have a closer look in the design. Here it is how it will look when we apply it in the facade. Here you can see the relation with the human scale. And let's talk more about dimensions. Our model will have a height of 60 centimeters and the distance between the plants and the PV is approximately 20 centimeters. And now about the assembly. We have 3 main parts. The main load-bearing element of the PV, of the module, and then the plastic panel with the buckets in it, and the PV panel. If we take a closer look in the assembly, we will see that we will put metal rods in an existing facade, and then we insert rivet bolts in it. Then the back plate along with the PV support will be inserted in that and secured with hexagonal nuts. Then we assemble the buckets inside the plastic panel and we insert it again in the same bolts. Then we secure it again with hexagonal nuts and we cover it with plastic covers. Regarding the PV panel, it is placed inside a metal frame and attached with screws to another metal element that sets the connection with the main support. But are plants cool enough? We will have an experiment to find out. So, our main hypothesis is that the plants evaporate and cool down the backside of the PV. But in order to find how much this increased efficiency, we will have our experiment. The main context is the same as before. We have 2 different setups placed in the same height in the blind facades. Each one of them consists of 7 different modules, and the measures will be taken in the middle one. The conditions are going to be the same for both of them, and the results that we are going to compare is the electricity, the humidity, and the temperature. If the result is not fulfilling, we can optimize it more through the tilt of the panel in order to orient more towards the sun, in the height of the facade in order to go upper in the upper floors and concentrate more radiation, the size of the panel in order to find the better proportion between the shading of the plants and the energy absorption, the leaf surface of the plants in order to evaporate more, and the distance between the plants and the PV. Here is the first experiment regarding the angle and the size. So overall, we think that although there are maybe more efficient ways to cool down the PV, our product can indeed increase the efficiency and moreover add the benefits of the green in the city, such as the biodiversity and the reduction of the urban heat island effect. Overall, if you need healthy and happy residents, as long as with energy absorption in the building, you should choose the solar green.